I just want to go over some of the various ways we can note the derivative. So when we have function notation here, if we use this prime, this apostrophe here, that's one way we can express the derivative. So we would call this f prime of x. So here's what we would say for that. Or we could say the derivative of f with respect to x. So this notation is also, we call it prime notation, so we could also call it y prime, referring to the function as y or y equals. So we say it y prime, or we could say the derivative of y with respect to x. This is what I keep referring to as a Leibniz notation. The Leibniz notation, Leibniz is a famous mathematician, and he developed this notation of the dy dx, which is how you say it, dy dx. And it's supposed to resemble a fraction, and it's supposed to then kind of help you remember that the derivative is an instantaneous rate of change. It's a rise over a run, so to speak. So we can say the derivative of y with respect to x. We could use the function notation again, so we could say df dx. Df dx is kind of how it sounds, or the derivative of f with respect to x. And then we could use the full function notation, df of x dx. So d df of x, or d dx of f of x. So d dx of f of x is how we could say that as well. And that would be the full function notation. So those are the different notations you can use. They all mean the same thing. They just mean the derivative of f with respect to x. So you can use any of those notations. The top two or the top three are really the most popular ones to use. So we're going to talk about velocity, speed, and rates of change as we're working with the idea of this derivative here. So our essential question for today is, what does the rate of change physically represent? And so when we go back to section 2.4, we have the rate of change. And that's the slope of whatever is changing. So for instance, the average rate of change is what we call our algebra slope. So average, you need 2 points. So this is our rise and that's our run. So there's no calculus involved. You have your 2 points, your beginning and your end. Then there's the instantaneous rate of change. The instantaneous rate of change is when we do the limit method. It's if we have that physical picture again, it's when we take the limit of h goes to 0. So we bring the 2 points together and we get that 1 point, and we find that tangent to the curve at that 1 point. So that's where we involve the calculus. It just takes a single point, and we think of that as the derivative. So these definitions are true for any function that we have. And when we talk about the rate of change, x does not have to always represent time. It could represent some other quantity. So we're going to look at some examples. In this example, we're looking at the cross-section of a tree. And we know that when we look at a cross-section of a tree, we see these growth rings. So we're here at the first year at the center of the tree, with it being a little sapling. And realistically, we have, these growth rings are dependent upon the season. So a rainy season, these growth rings the tree's going to grow more. A dry season, the tree is going to grow less. Any damage that occurs to the tree, you're going to be able to see. But if we can get consistent growing patterns over the course of the tree's life, then we notice that these rings get skinnier as the tree grows. And so we're going to explain how that happens using this example. So we're going to find the rate of change of the area of the tree with respect to its radius. So in other words, how much is the area changing out here when the radius is big, and how much is the area changing in here when the radius is small. And then we're going to find exactly a numeric value for that. So we need a rate of change, which means we need a derivative. So when we're talking about an area of a tree, which is a circle, we've got the area of a circle being pi r squared. We want the derivative of the area with respect to variable r. Now we're used to taking derivatives with respect to x. This is no different, it's just a different variable r. So we know pi is a number, so we can think of pi as like a 3. So we're going to do the power rule on our r, bring the 2 down, multiply it out front, and reduce the power. So our derivative, dA dr, equals the derivative with respect to r of pi r squared. So we're going to go ahead and bring that 2 down, multiply it times pi, reduce the power on r, so it's just r to the 1 power. So our derivative of the area with respect to the radius is 2 times pi times r. And so that we refer to this expression, this 2 pi r, as the instantaneous rate of change of the area with respect to its radius. So the farther I go out, the bigger this number is. So we're going to look at that in a little bit. For this specific example, when the radius is 5 inches, so I'm coming out here 5 inches, then my instantaneous rate of change of my area is 2 times pi times 5, or 10 pi square inches per inch. So if we look at the instantaneous rate of change of area with respect to radius, dA dr, we have an area over a radius. And so we have an area here, inches squared, over a length dimension, inches. If we evaluate that when the radius is 10 inches, that's supposed to be a 0, then we have 2 times pi times r, which is 2 pi times 10, 2 pi times 10. And so we have 20 pi inches squared per inch. So if we look at this as the radius gets bigger, the instantaneous rate of change of the area with respect to the radius gets bigger. Let's take a look at what that means. So here is that expression, rate of change is 2 pi r. So we're looking at this getting bigger as the radius increases. When it's 5, it's 10 pi. When this is 10, it was 20 pi. So that number is getting bigger. So if we look at maybe out 5 years here, out 5 rings, we have this ring that represents the growth of 1 year. Right? This is where we get into the counting of rings to determine how old the tree is. So we count the rings out here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we look at this region between a set of rings, and that's how much growth occurred in that year. So as we look out then to a later year, this number is going to get bigger. But what we know, in terms of studying trees, that the older the tree gets, the amount of area that is part of this ring, so this purple area compared to this green area, that's actually a constant area. So if we think about that, even though this number is getting bigger, this purple ring and this green ring represent the change in area. And the change in area is this dA portion of the derivative. So the change in area is actually constant. This is what's been studied with growth rings. And so if this number is getting bigger and this number is remaining constant, in other words, the green area and the purple area are the same value, then the only way this can get bigger is if the change in the radius gets smaller. And that change in the radius is the ring thickness. So if you think about looking at rings in a tree, as you go out to the exterior points of the tree, the rings get a lot skinnier. And that is because the tree is growing or adding on the same area each year, but it's adding it on around a bigger radius. So it's making that donut skinnier. So what's happening with tree growth is that if the change in the area, dA, is constant, then the rings must get closer together as that tree gets older. So that's an example of tree growth where we can use that derivative to talk about the rate of tree growth in a particular year. We also use the idea of an instantaneous rate of change for motion. So let's consider a position versus time graph. So here's your position with respect to time. We start at position A and we end at position B. Our displacement then is going to be these y values. So it's going to be the B position minus the A position. If we want to talk about average velocity, that's going to be an average rate. So if we notice our average velocity is our change in position over our change in time, it's our algebra slope. So it's our rise over our run. So again, we're seeing that key term average. So average velocity, velocity being a rate. This is our average rate. It's our algebra slope. And so we can find that average rate by taking the function values and taking their difference over the change in time. And we can represent it on a graph by drawing that line, that secant line between 2 points. The speedometer in your car doesn't measure average velocity, but it measures instantaneous velocity, right? As you drive a car, your speedometer changes all the time. So that's the velocity at one moment in time. So the instantaneous velocity is going to be the derivative. It's going to be our slope or our steepness of our curve right at a single point. Okay, so that's that limit process. It's going to be taking the limit of that slope as the delta t goes to 0. That's your h. So we call the instantaneous velocity then v of t as the first derivative of the position. So it's the steepness of that position function or the slope of the tangent line. So here's your instantaneous velocity. That should say instantaneous. Here's your instantaneous velocity at point A. So since velocity is a rate, it's the instantaneous rate of change of position, then we call it the first derivative of position. We also define speed, the thing you see on your speedometer, as the absolute value of your velocity. So we have to first get a velocity value by using the derivative, and then we can take its absolute value. In other words, speed is always positive, it's never negative. So we have some definitions for derivatives for motion, and we have velocity, which is the instantaneous rate of change of position. It's the first derivative. And speed is the absolute value of that. So let's talk real quick here. This is a short discussion. It's not in the notes, but let's just talk a little bit about motion here. And for instance, let's talk about free fall. So the free fall equation is a little physics here. We're going to talk about free fall. We know that g, usually we're used to the metric system, is 9.8 meters per second squared. Here's g in centimeters, and here's g in feet per second squared. So this is just different. Obviously, this bottom one here is the metric system, and this top one here is the English system. The weird thing is about physics. Physics uses the metric system most often. In calculus, we use the English system, and I don't really have a good explanation as to why, but we do. So our free fall equation is position equals 1/2 gt squared. So when we're talking about free fall, we're really talking about dropping something. So when we talk about dropping something, we're talking about it starting from rest, which is why we just have this acceleration term. And so using the English system, that is 1/2 times 32t squared, or 16t squared. So that's in calculus. That's what we think about as our free fall equation. Notice it's positive. We just call down positive, basically, is what we're doing there. So since velocity is the first derivative of position, we're going to take the derivative of this with respect to time. So I mentioned a little earlier, we're pretty comfortable with taking derivatives with respect to x. Now we're changing the variable since we're adding kind of a physical significance to the derivative. And so now our variable that we're doing the power rule on is t. So we bring down the 2, multiply it times 16, get the 32, and reduce the power. So we have 32t to the first power. So that's our velocity function. That's our first derivative of our position. So if we kind of extend that then to higher order derivatives, we know acceleration is also a rate. It's the rate of change in velocity. So it must be the derivative of velocity. So if we look at our acceleration being the first derivative of velocity, then if we talk about higher order derivatives, velocity is itself a derivative. So it's the derivative of a derivative. So it's a second derivative of position. For example, if velocity is 32t, what we got from the previous screen, then if we take the derivative of 32t, we get 32, which is our acceleration, which is our free fall number. When we talk about the units, if position is in feet, then velocity would be a rate of feet, a rate of change of feet, so feet per second. And acceleration would be feet per second, which is feet per second squared. So here we have derivatives of motion in particular. Our acceleration is the first derivative of velocity and the second derivative of position. And we have our English units here for g and our metric units for g. And then we have our, in English units, we have our possession equation here, 16t for free fall squared, and in metric, 4.9t squared for free fall in the metric unit. So let's just talk in general terms here. We have this relationship between a position graph, a velocity graph, and an acceleration graph. So if this is position, and it's not really a function, it's just kind of something made up here. If you notice, I've got a little bit of curvature at the beginning. I have something that looks pretty straight or pretty linear in the middle here. I've got more curvature here coming up to a hill, so to speak, a maximum, and then coming back down again, and then maybe a little straight portion here, a curved portion here, and a horizontal portion here. So we're going to kind of explain what's happening here in terms of velocity and acceleration. So right here in this curved portion, we've got acceleration is positive and velocity is positive. So we call this, it looks like we're gaining position at a faster rate. So we must be accelerating with positive velocity. In this middle section here, like I said, that looks pretty linear. So if that's pretty linear, then we have a kind of a constant rate of change of position. So we must be moving the same amount every second we move. And so that's going to be zero acceleration and constant velocity. And then in this area here, we seem to be not gaining as much position over time. So here we have negative acceleration with positive velocity. So we must be what I call slowing down. So when I look at this first portion all the way up to this maximum here, I look at this smiley face here as a speeding up, and then a constant velocity, and this getting flatter here is a slowing down. So this is getting steeper, speeding up, flat, constant velocity, getting flatter, slowing down. Okay, then this location here, instantaneously, since we have a horizontal tangent, we have zero velocity. And if we're slowing down to a stop here, then we must be changing direction and going in the opposite direction. So we have acceleration that is causing us to start to go back to where we came, which is why our acceleration would be negative there. And then in this portion right here, after we've turned around, we're going to start speeding up again in the negative direction. We're going to start coming back to where we started. So this curve is getting steeper. So we know we have a speeding up, and it's also coming back to its original position. So we know it's negative direction. And then this portion right here, it looks pretty linear. So again, we have constant velocity and 0 acceleration. And then this location here, we have the graph getting flatter, so we must be slowing down. So if we're slowing down, if we have negative velocity, then we must have positive acceleration. And this being flat, we must, since this is a constant position, in other words, we're not going anywhere, we have 0 acceleration and 0 velocity. So we're going to start looking at this. This is the first time we've looked at this sort of relationship, so if this is all a little confusing, don't worry too much about it. This is going to be a multi-chapter process here as we start to look at these things. Let's use the idea of a derivative to talk about this particle motion problem. We have a particle that moves along a line. The position at any time is given by the function t squared minus 4t plus 5, where s is measured in meters, so the position is measured in meters, and time is measured in seconds. So it says find the displacement after the first 10 seconds, the average velocity over the first 10 seconds, the instantaneous velocity when t equals 7. I want you to change that in your packet. I think it says 5. I'd rather have it be 7. The acceleration also when t equals 7, so change that in your packet. And then at what value does t have to be for the particle when the particle changes direction? So let's start with that first question, displacement for the first 10 seconds. So that phrase, the first 10 seconds, implies that we're starting at t equals 0 and ending at t equals 10. So this displacement then is the final position minus the initial position. There's no calculus involved at all. We just need to know what our position is at 10 and what our position is at 0 and subtract them. So when we plug 10 into the position function, we get 10 squared minus 4 times 10 plus 5. When we plug 0 into the position function, we get 0 squared minus 4 times 0 plus 5. And when we do that math, we're going to get, this is going to be 65. This is going to be 5. So we're going to get 65 minus 5, which is 60 meters. So our displacement in the first 10 seconds is 60 meters. Part B is find the average velocity over the first 10 seconds. So again, over the first 10 seconds implies that we're starting at t equals 0, ending at t equals 10. So that's 2 points in time. The term average velocity, average again is implying that's an algebra. Velocity is a rate. So this is your algebra slope here. So we have our displacement over our time. Our displacement from part A was 60. So 60 divided by 10 is 6 meters per second for the average velocity. Part C is the instantaneous velocity when t equals 7. Remember, we changed this value for this problem. So instantaneous velocity means the velocity at a specific point in time. That point in time is 7 seconds. So this is your calculus derivative here. Velocity is a rate, and it's the rate of change in position. So we need to take the derivative of the position equation. So that's our s prime, and we want to evaluate that when the time is 7. So finding our s prime, finding our derivative here, using the power rule, we're going to have 2t minus 4 for the derivative. And then we're going to put in when t equals 7. So when t equals 7, we have 14 minus 4, which is an instantaneous velocity of 10 meters per second. And that's the same as saying that the velocity is 10 meters per second, because that first derivative is the velocity. For part D, we want the acceleration when the particle is 7 seconds into its trip. And so for the acceleration, we need to take the derivative of the velocity. And the derivative of the velocity using our higher order derivatives is the second derivative of our position. So when we take the derivative again, that derivative ends up being 2. It's just a value. So that's a constant value. It doesn't change. There's no t expression here to plug a t value into. So when we're 7 seconds into the trip, we have an acceleration of 2 meters per second, or 2 meters per second squared. And so that's our instantaneous acceleration. And that is a constant. It's just a number, like I said a few seconds ago. So that acceleration is valid for any time in the trip. The last question is at what values does the value of t, at what values of t does the particle change direction? So changing direction is when the velocity is equal to 0. And so the velocity is the first derivative of the position, so we have to take this derivative and set it equal to 0. So and particle changes direction when velocity changes signs. In other words, when you're changing from going positive to going negative, you're passing through a velocity of 0. So we need the first derivative equal to 0, and our first derivative is 2t minus 4. So when we set that equal to 0 and solve for t, we get t equals 2. So that means that at 2 seconds, we know the particle is changing direction. And the particle is changing direction from left to right at time t equals 2. So how do we know that it's going from the left to the right? So that's kind of something for you to think about. The next example is a projectile motion example. So we have some dynamite blast propels a heavy rock straight upward. It launches it at 160 feet per second. It reaches a height that follows the basic rule of 160t minus 16t squared after t seconds. So it says, how high does the rock go? And then what is the velocity and the speed of the rock when it is 256 feet above the ground? What is the acceleration of the rock at any time t during its flight? And when does the rock hit the ground? So if you think about this blast, it launches a rock upward. Obviously, whatever goes up has to come down. So eventually this rock is going to slow down, stop, and start accelerating downward and hit the ground again. So how high does the rock go? Let's talk about that first. So we're talking about finding the top of the parabola, basically, as this rock is traveling up and coming back down. So if we think about it, this rock is traveling up, and that's where we want to know the information, is how high does that rock go when it starts to come back down again. So if we think about this from a calculus standpoint, that top point there is when we have a horizontal tangent. So that's when that slope of the curve is horizontal. And of course, if I say slope, you're probably already thinking derivative. So we have to find where the derivative is equal to 0. So that being the case, we take the derivative of the position here. So 160 t, the derivative is 160, minus 16t squared, bring down the 2, we get minus 32t to the first power. So we set that equal to 0, and that's this location here because that's the location we know that has a horizontal tangent. In other words, a tangent with 0 slope. So when you solve that, bringing the 160 to the other side and dividing by 32, the rock is at its highest point 5 seconds into the trip. And we know parabolas are symmetrical. So we probably know that if the rock is at its highest after 5 seconds, then it's going to hit the ground again how many seconds later? So kind of think about that as we go through this example. How high is the rock in the air? So answering the question now, after 5 seconds, we want to know the rock's position. That's what we're really saying. So we're going to plug a 5 in for the t's, and we have 160 times 5 minus 16 times 5 squared. And so that we know the rock is 400 feet in the air, which is quite a blast, actually. For part B, it wants to know the velocity and the speed of the rock when it is 256 feet above the ground. So remember, the speed is just the absolute value of whatever velocity answer we get. So to get kind of a picture of this, here's the path the rock takes. The top, we know the top is 400 from part A, so we'll put 256 about here. So what that's saying is that we need to take this position equation and set it equal to 256. I'm going to bring the 16t squared and the 160t over to the left, and it looks like I can divide by 16, so I'm going to go ahead and try that, and that works okay. And now I can factor this. So that is t minus 8 and t minus 2. that makes it factorable. And so when the time is 2 seconds and the time is 8 seconds, then we know the rock is here and the rock is here, 256 feet above the ground. So if you think about it, the rock has to hit that level going up, and then it hits that level again coming back down. So if I want to know the velocity at those locations, I need the first derivative of the position. So if the position is 160 minus 16t, 160t, excuse me, minus 16t squared, the first derivative of this is going to be 160 minus 32t. And now I can plug in my time values to find my velocity. So when my time is 2, which means the rock is right here, it's on its way up. The velocity then at 2 is 160 minus 32 times 2, which is 96 feet per second. And it's positive because the rock is going up. So the speed is also 96 feet per second because the absolute value of that would be the same value. At 8 seconds, what's happening with the rock is now it's on its way down. So when the time equals 8 seconds, we come back to our velocity expression. 160 minus 32 times 8 is negative 96. And you probably could sense the symmetry here. What happens going up also happens coming down. So what gravity takes away, gravity gives back, basically. So the velocity of the rock at 8 seconds is 96 feet per second downward. That's what the negative is for. And so when we talk about the speed on the next slide, that would still be a positive 96 because it's the absolute value. So there are the two velocity values. So if those are the velocity values, taking the absolute value of both those gets us a positive 96 feet per second squared. So the speed basically is saying if I had a radar detector and I could shoot that radar detector at the rock, the radar detector would come back with a value of 96 feet per second. For part C, it says what's the acceleration of the rock anytime during its flight. So it's not giving you a time. We're being asked for acceleration, so we know we need the second order derivative here. So the second derivative then is negative 32 feet per second squared. So we notice that the second derivative is a constant value, which is why we don't need to know what time at all. We can find it at any time during the flight because it's constant, it's not going to change. So it's negative 32 feet per second squared, which is the value for free fall for G in English units. It says D is when does the rock hit the ground. So I kind of alluded to this a little earlier in the example. We want to know when basically its position is equal to 0. And so we can solve that algebraically. We can set that equal to 0. We're going to get two values for t as we factor out a 16t. We're going to set each equal to 0, and this t is going to be 0, and this t is going to be 10. And so I kind of alluded to the symmetry a little earlier in this example. We know it takes 5 seconds to get to the peak, so it must take 5 seconds to come back down, so it had to have been at 10 seconds until the rock hits the ground. So there's our 5 seconds, and then there's our 10 seconds. So at this point now you can go ahead and start the homework for 3-4 day 1. We have a day 2 that we'll talk briefly about tomorrow. So go ahead and get started on that, and make sure you're also working on stuff that is past due so that you can qualify to take the exam next week.